Hello everyone, welcome to the course Nature and Properties of Materials. In week 5, we'll talk about composite materials. This course is offered by Professor Vishab Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm your TA, Alka Changit, also from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will be helping you in solving your weekly assignments. Then we'll go through some lecture notes. Okay, so first question is what is reinforcement in grey cast iron? So your options are cementite flakes, graphite nodules and cementite spheroids. So in case of grey cast iron, you should remember what is the microstructure of grey cast iron. So there will be flakes of graphite which also give it grey appearance. Okay, and this also provided some mechanical properties that cast irons possess. So the correct answer here will be graphite flakes. Okay, and other options are for different type of cast irons. So cementite flakes and graphite nodules, cementite spheroids, these will be in nodular cast iron and other type of cast irons. So this is what microstructure of cast iron looks like. So here these gray parts, these are the graphite, and the other part around it is pearlite, and the single color part is the ferrite. Okay, so here explanation is given in cast iron and steel. Graphite and cementite work as reinforcement in a metallic matrix of ferrite or pearlite. So both are composite like structures. So in case of cast iron, you'll be having graphite, and in case of steel, you'll be having cementite as reinforcement. And pearlite is also a composite like structure because in that case, you'll be having ferrite as matrix, softer matrix, and cementite layers, lamelles as the reinforcements. Okay, so for grey cast iron, graphite is in flake form, while in steel, cementite is present as reinforcement. Next question is the continuous phase of a composite material is known as its and blank. So you have to fill in the blank with options such as dispersed phase, reinforcement phase, matrix phase or fiber phase. So the continuous phase of composite material is known as matrix because it will be continuous. Matrix is always chosen for the softer phase which is continuous. So third one will be the correct option. So composites are mainly made with the help of two parts. First will be matrix, which is continuous phase, and discontinuous phase will be reinforcement, which will be having higher stiffness and higher ductility, no, higher stiffness and higher hardness, and it will be providing shrink to your material. Next is so the explanation being composite materials contain mostly two phases, matrix and dispersed phase. The matrix phase is continuous, which tends to bind the fibers together, and it also protects them from damage and is used to transmit the load. So at the interface, some of the load is transferred to these fibers or particles, okay, which has higher strength, and this matrix will also be carrying some load. Next is the which of the following materials are common for whiskers. Your options are graphite or silicon carbide, glass and boron, steel and tungsten, and polymers and ceramics. So the correct option here will be first one. Okay, so whiskers are thin single crystals which have extremely large length to diameter ratio, and due to their small size they have high crystalline perfection. And the fibers, so fibers are polycrystalline materials of small diameters, whereas wires have large diameters. The common materials are graphite, silicon carbide, aluminum oxide, etc. Glass, polymers and boron, they fall under the category of fibers. Steel, tungsten and molybdenum are commonly used as wires. So this is what your composite will look like, and this continuous phase will be reinforcement, and continuous phase will be matrix, and this continuous phase will be fibers. Next is, which of the following statement is true? Your options are higher grain boundary increases strength, grain refinement increases ductility, composite strengthening is related to grain boundary, and single crystalline material has high grain boundary area. So out of these you have to find out which statement is correct. So we need to, so firstly, single crystalline material won't be having any grain boundary. So this statement is incorrect. Then you have composite strengthening is related to grain boundary. So this is also false, because grain refinement or grain boundary strengthening is what related to the grain boundary. Then grain refinement increases ductility. So this is also false statement, because it doesn't deteriorate the ductility, but it decreases the ductility of a material. If you keep on increasing the grain boundary area in your material will start becoming more stronger, but it will show some diminished ductility, but not much. So first statement is the correct one. So it states that higher grain boundary increases strength. So as you keep on increasing the grain boundary area, so the moment of dislocation will become harder, and this will improve the strength of material. Okay, so here you can see okay, in this particular diagram you can see there are trains having different orientations, and between two different orientation you will be having some region which will be having very less order. So these less ordered areas in the material, these are the grain boundaries. Okay, and these grains, they are differently oriented crystals. So in explanation it is given that a fine grained material, one that has small grains, is harder and stronger than a coarse grained due to a greater total grain boundary area to restrict dislocation motion. And grain boundaries also act as source and sink of dislocation, but that is not a reason for the hardness enhancement in the metals. Next question is, below figure depicts the structure of which type of composite materials. So these are different directions of laminates are here. So this is a laminate type of composite material. So out of the other options such as discontinuous, aligned, dispersion strengthened and laminate will be the correct option. So in case of a laminar composite, it is a subcategory type of structural composite with a varying orientation for each layer. These composite materials are used for their high strength. Next is, which of the following is the correct size range of dispersoids in micrometers and dispersion strengthened composites? Your options are 0.0001 to 0.0009, 0.01 to 0.1 micrometers, 0.1 to 1 micrometer, 2 to 2.7 micrometers. So second one will be the correct option. So dispersoids and composites vary in size from 0.01 to 0.1 micrometer because they are very small. Their size is a important factor for mechanical properties, and fine size dispersoids provide that properties. So size as well as how the dispersors are distributed along the matrix, that also contains the particular mechanical properties that also decides that. Next is, which of the following is not a characteristic trait of composite materials? Your options are high strength, toughness, modulus, lightweight, easy to assemble, or sensitive to temperature change. So out of these, which is the correct option? So your question is, which of the following is not a characteristic trait of composite materials? Your options are high strength, toughness and modulus, lightweight, easy to assemble, or sensitive to temperature change. So correct answer will be fifth one. Okay, so in case of composite materials, you have matrix plus reinforcement, and here reinforcement generally provides a composite with more strength, stiffness and toughness due to the crack bridging. So crack bridging is one of the toughening processes. So in this case, as your crack keeps on propagating, when it comes into contact with the reinforcement, it has to deflect its direction, and that requires a lot of energy, which leads to toughening of material. Because the crack length, as it keeps on increasing, it requires more and more effort and load for the fracture of the ultimate fracture of material. So composite materials, they have great mechanical properties, corrosion resistance, and are easy to assemble, and they are light in weight in case of fiber composites, and they aren't very sensitive to thermal shocks and temperature changes. However, they are more expensive than conventional materials. Next is, what type of material is often used in creation of soft actuators for soft robotics? Your options are shape memory alloys, carbon fiber, nylon and aluminum. So here correct answer will be first one, SMA or shape memory alloys. So shape memory alloys work great as actuators for soft robotics. Example, nitinol. And these shape memory alloys, they convert thermal energy into mechanical energy, making them desirable for making actuators. Next question is, chain polymerization mechanism may occur due to. Your options are cationic, anionic, only due to free radical and cationic mechanism, or all of the given options. So correct answer here will be all of the given options. Okay, so free radical polymerization is a type of chain growth polymerization along with anionic, cationic and coordination polymerization. And free radical polymerization is a polymerizing approach by which successive addition of free radicals take place to form a polymer unit. Next question is, which of the following may alter the mechanical properties of reinforced? Your options are constituent properties, fiber length, fiber orientation, or all of the mentioned. So explanation here is that constituent properties, fiber length, fiber orientation, etc. affects the overall property of reinforced composites. And here, with changing fiber length, you can see how the various properties change. So the blue one is impact. So impact strength will keep on increasing with increasing fiber length. And the strength will also increase. Modulus will also increase. but processability will keep on decreasing as the fiber length will keep on increasing. Okay, so all these options, they affect the overall properties of reinforced composites. Next is particle reinforced composites. They have which type of strengthening? Your options are strain hardening, grain refining, edge hardening, or dispersion strengthening. So here particle reinforced composites, they have which type of strengthening? So particles, they are basically having a separate interface, so they are dispersion strengthening. So second phase type of strengthening can be of two types, either edge hardening. In that case you'll be having some compatibility with the matrix and there will be not very sharp interface. As in case of dispersion strengthening, there will be sharp interface in between the strengthening particles and the matrix. Next is which one is not the role of fiber in composites. Your options are to relieve stress, to enhance strength, or to provide crack bridging, or to enhance thermal resistance. So the correct option here will be to relieve stress. Okay, in case of fiber, it will also provide good strength to your material by taking some part of the load that is applied on the material. Also, if crack is propagating, it will be bridging the crack. So crack length will keep on increasing and it will require more and more load for the ultimate fracture of material. And also it will enhance thermal resistance of material and it won't be relieving any stress. Next is which material has at least L by D ratio, length divided by diameter ratio, equal to 10:1. So your options are viscous, fibers, rods and wires. So out of these, fibers are the ones that will be having L by D ratio at least 10:1. So the diameter will be higher in case of rods and wires, and viscous it will be very smaller compared to fibers. Next question is, what is the disadvantage of metal matrix composites? So your options are lower operating temperature, flammable, costly, or low resistance to organic fluids. So metal matrix composites, they are costly compared to the polymer matrix composites and ceramic matrix composites because the processing is also very complex compared to other type of polymers. And other options such as low operating temperature, so their operating temperatures are higher compared to polymer matrix composites and they are not flammable as polymer matrix composites, and they also have low resistance to uh, organic fluids is also not one of the disadvantage for these. Next is which is not a disadvantage for pultrusion method for fabricating composites. Your options are cheap die requirement, automated processes, high speed, continuous reinforcement. So out of these, the advantage, others are some of the advantages for this method such as automated processes, high speed and continuous reinforcement, but cheap die requirement is not the one of the advantage for this. It requires costly dies for forming. Next, next is now the definition of composites. So natural or artificial mixtures of two or more distinct phases or constituents. So there will be matrix and reinforcement. It will be consisting two different type of phases or constituents. And it can be mixtures that may consist of metals, polymers and ceramics. And the primary engineering goal is to achieve a better balance of properties from the combination of materials. And here you can see different type of parts of your airplane can be made of different type of materials. So these all different colored materials are some of the composites. So red one is for carbon atomic sandwich, and orange is for carbon monolithic structures. This light blue is Kevlar or Nomic sandwich, and dark blue is Kevlar Nomic sandwich with siphoning carbon piles, and the yellow one is for fiberglass or Nomic sandwich. The cabin floor panels are made with the carbon or Nomic sandwich, and the propeller blades are made with the fiberglass, polyurethane foam and carbon spar. Next is in history also we can see some of the uses of composites. So in Indus civilization, which was around 3000 before Christ, and at that particular time straw reinforced bricks were used. So here also in picture you can see these straws are used, and with the help of clay or soil this is used, so that will be acting as matrix, and this straw will be acting as reinforcement. In Hittites and the samurai around 100 before Christ, steel composites were used, and it was formed by the repeated folding of a steel bar back on itself. An industrial revolution occurred between 1800 AD, and it used concrete and cast iron. And in modern composites from 1950 to present we can see fiber reinforced composites. Now in case of natural composites also, it exists throughout the nature, and almost all natural materials are in form of composites. Some of the examples include wood. So wood is made with the help of lignin matrix and hemicellulose wound in the spiral form. And bone is made with the organic fibers plus inorganic crystals and water and fats. So 35% of bone consists of organic collagen, protein fibers with small rod-like hydroxyapatite crystals. So in this wood also we can see different parts. So in center you can see pith, then heartwood, and then sapwood, and then growth rings, radial surface, transverse surface, etc. Next is cast iron, which is also a composite. So it is an alloy of iron and carbon, but after the microstructure, you notice the microstructure, it consists of graphite flakes which act as reinforcements, and the matrix consists of mainly iron consisting matrix, so it is matrix. Then in cast iron and steel, graphite and cementite respectively, they work as reinforcement in a metallic matrix, so both are composite like structures. Here also in case of nodular type of structure, you can see these nodules which will act as reinforcement, and the other part will act as matrix. Classification of composites. So these mainly can be of the type of particle reinforced or fiber reinforced or structural type of composites. In case of particle reinforced, they have large particles, and then there are dispersion strengthened type of particle reinforced composites. So Next is fiber reinforced. Then in case of structural, there are laminates type of composites, but there will be different direction oriented laminates which will be consisting interface at the joints, and because of their different orientations also it will be providing different type of properties to your composite compared to if this layer had been same throughout the thickness. So this is unidirectional and this is cross bind. And next type is sandwich structure. Next is large particle composites. So in this case, examples include concrete, which is composed of cement, the matrix, and sand and gravel, which consist of the particulates. And the particulate phase is harder and stiffer compared to matrix. And the reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle. The matrix transfers a fraction of the applied load to the particles, and it shows improvement in the mechanical behavior, which depends on strong bonding at the matrix particle interface. So here we can see in case of concrete, cement plus sand, stones and water, they combined create composite called concrete. Next is dispersion strengthened composites. So in this case, particles are normally much smaller with diameter between 10 to 100 nanometer, and the strengthening occurs on the atomic or molecular level. The matrix bears the major portion of an applied load, while the small dispersion particles hinder the motion or dislocations. Thus, plastic deformation is restricted such that yield and tensile strengths as well as hardness improves. Examples include sintered aluminum powder, which includes flakes of aluminum coated with aluminum Al2O3, which are dispersed within an aluminum metal matrix. Okay, so here also, and this particular discovery was done by accident. So as they were trying to ball mill the aluminum powder, so there was formation of some alumina layer above this, so alumina formed, and then it also got sent it also got ball milled and then sintered, and it showed higher strength compared to pure aluminum. So that's how the alumina, this sintered aluminum powder was found, and after that this particular type of strengthening was used. So here also you can see the formation of dislocation, and if this dislocation is coming closer to this strong particle which is less than 100 nanometer size, then this particular particle will be having stress field of dispersion, and then this particular particle, this dislocation will come closer to this particle, then this dislocation will be stopped, and this particle will act as barrier for this dislocation movement. Next is fiber reinforced composites. So firstly we'll talk about fiber phase, then we'll go to the matrix phase. Firstly, on the basis of diameter and character, so fiber phase can be grouped into three types: whiskers, fibers and wires. So in case of whiskers, there are very thin single crystals that have extremely large L by D ratio, but they have the form of fiber, and there is and these whiskers, they are flow free, so there are very less defects and they are extremely high in strength, but they are very expensive. And these include graphite, silicon carbide, silicon nitride and aluminum oxide, etc. In case of fibers, a material which has at least L by D ratio equal to 10:1. So either they are polycrystalline or they can also be amorphous in nature. And generally polymers and ceramics, they are used as fibers. Then there are wires which have relatively large diameters, and typical materials which include steel wires, molybdenum wires and tungsten wires, etc. Next is matrix phase of fiber reinforced composites. So in this case, the role of matrix in composites includes binding fibers together, and they also protect the individual fiber from damage by the external environment. So if you are using fibers as by combining without using any matrix, then it will be showing less of these properties compared to when you use it in composite. So it acts as a medium to transmit and distribute externally applied stress to fibers, and it also serves as a barrier to crack propagation. Requirement of composites. So the matrix material should be ductile and the elastic modulus of the fiber should be much higher than that of the matrix, and there should be adequate bonding between the matrix and fibers. And the role of the fibers in composite includes so some of the roles of fibers. Firstly, they enhances the stiffness, and so the stiffness of the matrix will always be lower compared to the stiffness of composite. And also it enhances the strength and also provides crack bridging. As I told earlier, the crack will be deflected to enhance thermal resistance. So thermal resistance is also enhanced. Then requirement of composite. So the matrix material is always ductile compared to the fiber phase for providing better mechanical properties. Elastic modulus of fiber should be much higher than that of the matrix, and so elastic modulus of also should be higher for your fiber compared to matrix, and there should be adequate bonding between matrix and fiber. So if there is if delamination is a process where the matrix and fiber they have interfacial energy very high, so if you are applying any load, these fibers will delaminate and this composite won't act very good in loading conditions. So that's why this bonding should be good for proper composite. Now there are stress strain curves. So firstly, for matrix, your matrix is always ductile in nature, having lower strength and elastic modulus. So this one would be matrix. So elastic modulus of matrix is given as EM, and for fiber it is given as the red one. Okay, so here you can see it's brittle, so its elastic modulus is also higher, shown as EF, and its tensile strength is also very high. Okay, so here brittle fiber fracture strength is given and ductile matrix fracture strength is very lower compared to that. Then on plotting the stress strain curve for the composite, you can see its failure occurs at the medium stress. So your material will be having the properties in between fiber and matrix properties. So its elastic modulus is somewhere in between, and its fracture strength is also somewhere in between. Okay, and there are two stages are given. So for primary primarily it's showing elastic type of behavior, then it will be showing some permanent deformation. Then we have volume and weight fractions. So if VF, VM and VV and VC, these are the volumes of fiber, matrix, void and composites. So VF will be, small VF will be equal to volume of fiber divided by volume of composite. Okay, so this will be fiber volume fraction. Then small Vm will be matrix volume fraction. So matrix volume divided by volume of composite. And void, volume of volume fraction of void. So it will be volume of void divided by volume of composite. So here Vf, Vm plus Vv, these all combined addition will be equal to, these are all fractions, so so addition will always be 1. And if you combine volumes, so entire volume will be equal to volume of composite, which will be equivalent to volume of fiber plus volume of matrix plus volume of voids. And when you count the weight, so voids won't be having any weight, so void will won't be here. So here you have just volume fraction of fiber, so it will be, sorry, weight fraction of fiber is equal to weight of fiber divided by weight of composite, and weight fraction of matrix will be weight of matrix divided by weight of composite. Here WF plus WM will be equals to 1. Okay, so fractions will be again equal to 1, and the weight of composite will be equals to weight of fiber plus weight of matrix. And also weight can be written in terms of density. So rho is density of composite times volume of composite will be equals to density of rho F times VF plus rho M times Vm. Now it can be written in terms of fraction as well. Next is longitudinal modulus. So in this case the tensile load is acting along the fiber direction. Okay, so here you can see this is the direction and this is the fiber orientation. So here your tensile load is acting along the fiber orientation, and when it will be acting perpendicular, this is the direction of fiber and this is the direction of loading, so it is 90 degree. So then it will be transverse modulus. So in case of longitudinal modulus, the tensile load is acting along the fiber direction and assuming perfect bonding between fiber and matrix. So it can be given as all the strain in the matrix and fiber and composite will be equal. So how much should be stretching it in this direction? The strain in fiber and matrix and composite all will be equal. Okay, this one will be one of the relation. Then these are all the longitudinal strains in fiber, matrix and composite respectively. And the tensile load rho C applied on the composite lamina is shared by fiber and matrix. So rho C PC will be equals to PF plus PM. Here PC is the load on the composite equals to load on fiber plus load on matrix. Therefore, so you can write this in terms of stress and area. So sigma, as we know, it is load divided by area. So sigma C times AC will be equal to sigma F times AF plus sigma M minus sigma N times AM. Okay. Now you can divide all this with the AC, then you'll be getting this equation. And we already know AC will be equal to AF plus AM. Then you can write it in terms of elastic modulus. Okay. So elastic modulus longitudinal will be equals to EF times VF plus EM times VF. Next is the tensile load is when it is acting normally or perpendicular in the fiber direction. So in this case, all your loads will be equal. Okay, rather than strain, here loads will be equal. So sigma F equals to sigma M equals to sigma C. Okay, and this can be rewritten using Hooke's law as sigma C. Firstly, okay, the strain or deformation of the entire composite can be written as this. Okay, so EC will be equals to EF times VF plus EM times VM. And this can be rewritten using Hooke's law as sigma C upon EC equals to sigma F upon EF times VF plus sigma M upon EM multiplied by VM. Here sigma F, these all are equal in above equation, so we can put it here and we can find 1 upon EC equals to VF upon EF plus VM upon EM. So here easy transfers you can write in this form, EF times EM divided by EF VM plus EM VF. Now next is metal matrix composite. So here your matrix will be any ductile metal using alloys of aluminum, magnesium, titanium and copper. Okay, and the fiber will be, it can be carbon, it can be silicon carbide, it can be boron or it can be aluminum oxide, etc. The advantage include over PMC that it has higher operating temperatures, non-flammability and greater resistance to degradation by organic fluids. And demerit include metal matrix composites which are costlier than PMCs. These are some of the properties of some fibers. Okay, so firstly, these are some of the examples of fibers: carbon fibers, silicon carbide fibers, boron fibers, and aluminum oxide, etc. And advantages over PMC. PMC is polymer matrix composite. Now, in polymer matrix composite, what happens? That these are flammable because of addition of hydrocarbons, okay, which burn easily. And here these metals are non-flammable, and also polymers degrade very easily at higher temperatures, so they have low operating temperature, while in case of metal matrix composites you have very high operating temperatures as well. And also these have greater resistance to degradation by organic fluids. And demerits include metal matrix composites are costlier than PMCs, polymer matrix composites. And then properties of several metal matrix composites. So these are reinforced with continuous and aligned fibers, and the fiber and matrix are given and the volume is given, fiber content, and depending on that you can find out what will be their longitudinal tensile modulus and longitudinal tensile strength. Okay, so for carbon fiber and matrix 6061 aluminum, 6061 aluminum is one of the aluminum alloy. So if you are adding carbon fibers in it of the 41 volume percent, density will be 2.44 gram per centimeter cube, and the longitudinal tensile modulus will be 320 GPa, and longitudinal tensile strength will be 620 MPa megapascal. For boron fiber in 6061 aluminum, the 48 volume percent fiber content, you will be having 207 GPa of the longitudinal tensile modulus, and 1515 will be the tensile strength MPa. For silicon carbide fiber of 50 volume percent, density will be 2.93 gram per centimeter cube will be density, and 230 will be modulus, 1480 MPa will be tensile strength. Then you have alumina in aluminum alloy. So here you have 24 volume percent, and here also you will be having 120 GPa modulus and 340 MPa will be tensile strength. For carbon, in case of magnesium alloy AZ31, you will be having 38 volume percent of fiber content. For this you will be having density very lower compared to aluminum alloys, 1.83, and the longitudinal tensile modulus will be 300, which is very higher compared to these ones, and 510 will be tensile strength, MPa will be tensile strength. Next is boresic, and it in titanium matrix. So in this case, its fiber content is 45 volume percent, and the density is 3.68 gram per centimeter cube. The longitudinal tensile modulus is 220 GPa, and the tensile strength will be 1270 MPa. Applications of MMCs. So they can be used in making tank armors, golf clubs, space shuttle frames, and antenna boom for the Hubble Space Telescope, which is made of graphite fibers in 6061 aluminum. Next is polymer matrix composites. So in this case you have glass fiber reinforced polymers, and in this case you have matrix made of plastic, which is most often epoxy and polyester resin, and reinforcement will be consisting of glass fiber or e-glass, which has diameter from 3 to 20 micrometer, and this consists of typically 55% of silica, 16% of calcium oxide, 15% of alumina, 10% of B2O3, and 4% of MgO. And it can be easily drawn into high strength fibers from the molten state. The limitation for this is service temperature up to 200 degrees Celsius, above which polymer matrix starts to degrade. Applications include automotive and marine bodies, plastic pipes, storage containers, and industrial flooring. So because of polymer matrix, these are highly corrosion resistant as well. That's why they can be used in marine bodies. Okay, and the service temperature can't go beyond 200 degrees Celsius in PMCs because polymer, they start to degrade, and they can be easily drawn into high strength fibers from the molten state. So their melting temperature is very lower, so it's easy to cast as well. So for GFRP, which is glass fiber reinforced plastics, so for these fiber volume fraction can be 0.6, and the epoxy matrix, and here density will be 2100 kg per meter cube, which is lightweight. So, and tensile modulus will be, in longitudinal direction it will be 45, in transfer direction it will be 12. and in GPa, and tensile strength will be 100, 1020 in longitudinal direction, 40 transverse direction. Next is carbon fiber reinforced polymer, CFRP composites. Here matrix will be made of polymer resin and fibers will be made of carbon fiber reinforcement. The carbon is a high performance fiber material because highest specific modulus, they have very high specific modulus, meaning modulus divided by density. So this part is very high, and the specific strength of all reinforced fiber materials, they retain at elevated temperatures. So, and also at room temperature they are not affected by moisture and wide variety of solvents, acids and bases. The fiber diameters also normally ranges between 4 to 10 micrometer. Applications include carbon fiber wheel, Boeing 787 Dreamliner, nearly 50% frame of CFRP, mountains, bicycle frame, seats, racket, etc. All these are some of the applications of these CFRPs. And in case of CFRP, if the volume fraction is taken as fraction for fiber if taken as 0.6%, having epoxy matrix, then its density is 1600 kg per meter cube, which is again lightweight. The modulus will be 149 in longitudinal direction and 10 in transverse direction. The tensile strength will be 1240 MPa in longitudinal direction and 40 in transverse direction. Next is aramid fiber reinforced polymer composite. So these are used in making bulletproof vests as well. So trade name of most common aramid fiber Kevlar and Nomex trademark. And chemically, this group of materials is known as polyparaphenylene terephthalamide. Okay, and it is known for its toughness, impact resistance and resistance to creep and fatigue failure. And it has strong covalent bond axially, weak hydrogen bond transversely, and it has negative coefficient of expansion due to presence of kinks, and ultraviolet sensitive, and also it is ultraviolet sensitive, so it degrades. And typical application include ballistic products such as bulletproof vests and armors, and in making sporting goods, ropes, missile cases, replacement for asbestos in automotive, brake and clutch lining and gaskets. Ceramic matrix composites. So ceramics are highly brittle in nature, thus they have low fracture toughness. And in general, the fracture toughness of ceramics is from 1 to 5 MPa under root meter, while for metal alloys it is 20 to 90 MPa under root meter. So it is around 20 times higher. And by using ceramic matrix composites, fracture toughness can be increased to lie in the range of 6 to 20 megapascal under root meter. The crack initiation normally occurs within matrix phase, whereas crack propagation is hindered by the particles, fibers or whiskers. And they exhibit improved high temperature creep behavior and resistance to thermal shock. The brake disc of Ferrari race car, so it is also made using carbon fiber reinforced in silicon carbide matrix. Next are cermets. So cermet is made with the names ceramic and metal. So initial part cer and met, cermet. Okay, so in this case Your matrix will be ceramic and the other face will be metal. Okay, so in this case you have binding phase which is metal. So it can be made of nickel or cobalt. So composites of ceramic particles which are strong and brittle in a metal matrix. They are soft and ductile. So composites of ceramic particles which are strong and brittle in a metal matrix having soft and ductile. And this metal matrix is only up to 5 to 10 volume percent. It has very higher toughness and wear resistance compared to the traditional materials. And for instance, tungsten carbide and titanium carbide ceramics embedded in a matrix of a metal such as cobalt or nickel only about 10 to 15% of metal volume, and they are used for cutting tools, for hardened steels, electrical components such as resistors and vacuum tubes, valves, etc. And these are some of the ceramides that are used here. These are the made with the help of ceramides. Next is carbon-carbon composite. So in this case, both reinforcement and matrix are made of carbon, which are very expensive, and there is very high modulus of elasticity up to 200 GPa, and strains even retained at around 2000 degrees Celsius. The low density is here from 1830 kg per meter cube. So it also has high thermal conductivity around 100 watt per meter Kelvin, and it also has low coefficient of friction in fiber direction, and it also has high abrasion resistance. Applications include these missile cones and B-2 bomber aircraft, and in also wing leading edges of the space shuttle. Okay, so there are three types of composites. Then we'll go to the manufacturing processes of making composites. So in case of laminated composites, it is a laminate is constructed by stacking a number of laminae. So there are four types of laminated composites. First is unidirectional laminate. In this case, fiber orientation angles are the same in all laminates such as theta equals to 0 degree. So this direction change won't be there. All direction will be in same direction. All orientations will be in same direction. Next is angle ply laminate. So in this case, fiber orientation angle is alternate layers are theta minus theta, theta minus theta, where theta is equals not to 0 degree or 90 degree. Next is cross ply laminate. In this case, fiber orientation angle ply is given here. So it will be repeating in alternate layers. Okay, cross ply laminate. So the fiber orientation angle in alternate layers are 0 degree, 90 degree, 0 degree, 90 degree. Symmetric laminate, it is identical ply in material thickness, the fiber orientation angle at an equal distance about the center line. So here theta z will be theta minus z, where z is the distance from the midplane of the laminate. Next is sandwich panels. So it consists of two strong and stiff sheet faces that are separated by a core material or structure. It combines relatively high strains and stiffness with low densities. Outer sheet can be made with the aluminum alloys, fiber reinforced plastics, titanium, steel or plywood, and the core materials can be made of rigid polymeric foams such as phenolics, epoxy, polyurethanes, or wood such as balsa wood, and honeycomb such as hexagonal cells. Next is sandwich panels. It can be of low water absorption, good anti-corrosion, good thermal insulated capacity. So these are some of the advantages of sandwich panels. And here also you can see this honeycomb type of structure is sandwiched in between these sheets. And this is connected with the help of adhesives. These are the face sheets which will be facing the environment. Fabricated sandwich panel. Next is hybrid composites. So there are two or more different kinds of fibers in a single matrix. For example, using carbon fibers which are strong and relatively stiff, and they provide low density reinforcement, but they are expensive. Next is glass fibers which are inexpensive and they lack the stiffness of carbon. Okay, in case of examples include carbon fibers which is strong and relatively stiff, and it also provides low density reinforcement but are expensive. In case of glass fibers, they are inexpensive and they lack the stiffness of carbon. The glass carbon hybrid is stronger and tougher and has higher impact resistance. The fibers may all be aligned and intimately mixed with one another, or laminate may be constructed. Applications include baseball bat, ice skates, etc. In case of hybrid composites, two or more different kinds of fibers in a single matrix will be consisting, and these are the examples that we talked. Now, the manufacturing processes of composites. First is hand layup technique. So firstly, gel coat is applied to open mold. So here this orange colored is the gel coat. Okay, then to avoid the sticking of polymer to the surface, so this gel coat is applied. Then reinforcement is placed in the mold. So after this resin is applied, and then base resin is mixed with the catalyst is applied by pouring and brushing. So firstly you will be applying this dry reinforcement, then you will be pouring this resin. Okay, so layup is made by building layer upon layer to combine the desired thickness. And for an epoxy based system, the normal curing time at room temperature is 24 to 48 hours. And this method is mainly suitable for thermosetting polymer based composites. Advantage include low cost tools and versatile. This technique is versatile and it also uses low cost tools. Disadvantages include the time consuming, and it is also inconsistency in the product. And also there is easy formation of an air bubble, and also disorientation can also occur of fibers. Okay, and for an epoxy based system, the normal curing time at room temperature is 1 day to 2 day. Spray layup technique. So previously it was hand layup technique, and this is spray layup technique. So in this case it is extension of hand layup technique method. Here a spray gun is used to spray pressurized resin and reinforcement, which is in the form of chopped fibers. So two parts are there. So one will be supplying resin and one will be supplying catalyst. And here you will be applying again release gel, polymer resin and reinforcement. And then this spray gun will be used, and this roller will be used for providing even thickness. Okay, so this spray gun is used to spray pressurized resin and reinforcement, which is in form of chopped fibers. And the matrix material and reinforcement may be sprayed simultaneously or separately. Advantages include continuous process. Any material can be used as mold, and the error can be corrected by respraying. Disadvantages include that this is inconsistent method, and there is no control of fiber orientation, and only one side is finished, and also it is not environmental friendly. Next is pultrusion. So in this it is made with pull and extrusion. So firstly you'll be extruding your fibers along with resin, and you'll also be providing some pull for making these fibers. So it is automated process for continuous manufacturing of constant cross section profiles, and the profiles they have high strength in the length direction, and the principal reinforcements include glass, carbon and aramid fibers consisting of 40 to 70% volume. The matrix material include polyesters, vinyl esters and epoxy resins. Advantages include automated processes, high speed. So this process is also high speed and highly automated. It is also versatile cross-sectional shape, and it will also be providing continuous reinforcement. Disadvantage include the die that can be easily messed up, and it is also having expensive die, and it is mainly used in thermoset matrix. And this is the process. So here pullers are used for flattening this particular resin. Then there is curing die, then performing die, then resin impregnation tank, and then these fibers are rovings. So it will be coming from this direction. So these fibers will be dipping in this resin, then this resin will be on top of this, then this will be performing die, then after that curing, meaning it will be heated, these thermoset matrix, then these pullers will be providing particular shape. Next is pre-preg, then resin transfer molding. Okay, so in case of pre-preg, the fiber reinforcements are impregnated with a specific amount of epoxy resin system in a separate step before the layup. So in this so-called pre-pregging step, fibers are wetted uniformly and a pre-preg of high quality is formed. Advantages include orientation of fibers can be changed, and it is a consistent process compared to the other previous processes which were inconsistent, and it provides high productivity. So here you can see these are this is the direction. So firstly fiber reinforcement, fabric fibers are rolled and this epoxy resin is feeded, and after pre-pregging you will be cutting and laying up the sheets, and then it is pre-forming, then transfer pre-form into mold, then curing, and then opening and demolding. Disadvantages include continuous process which needs more customers, and it also has limited shelf life, and there is possibility of delamination. Next process is resin transfer molding. So it is also known as the liquid transfer molding process. In this case, dry fiber is preformed into the lower mold and the upper mold is fixed in place. Then low viscosity resin is injected under some pressure into the mold cavity where it spreads throughout the fiber. Advantages include design flexibility, low startup cost, faster production, good surface finish. Disadvantages include it has expensive tooling, it is also time consuming curing, it has also complex mold design. Okay, so here with the help of pump, resin and catalyst are mixed and it's provided in this mold. So there is inlet after mixing in chamber, that is inlet and outlet is provided. So it will be filled in this. There will be already presence of this fiber preform. Okay, then it is mixed with the resin and then there is heating. So curing will be taking place and then ejection will be for the finished product. Okay, so that's it from my side. I'll be again repeating the questions in some time. So first question was, what is reinforcement in grey cast iron? Your options were cementite flakes, graphite nodules, cementite spheroids. So correct answer here will be graphite flakes. So this is the microstructure of cast iron. Here you can see in cast iron and steel, graphite and Fe3C work as reinforcement in a metallic matrix of ferrite and pearlite. So both are composite like structures. For grey cast iron, graphite is in flake form, while in steel, cementite is present as reinforcement. Next is the continuous phase of a composite material is known as your blank. Your options are dispersion phase, reinforcement phase, matrix phase and fiber phase. So correct answer will be matrix phase. Okay, so in composite you can see matrix plus, it's made with the matrix plus reinforcement. So composite materials contain mostly two phases, matrix and dispersed phase. The matrix phase is continuous, which tends to bind the fibers together, and it also protects them from damage and is used to transmit the load. Okay, it can be seen here as well in the fiber reinforced composite. Next is, which of the following materials are common for whiskers? Your options are graphite, silicon carbide, glass and boron, steel and tungsten, polymers and ceramics. So correct answer here will be graphite and silicon carbide. Okay, polymers and ceramics are used for making fibers, not whiskers. So whiskers are thin, single crystals having an extremely large length to diameter ratio. Due to their small size, they have high crystalline perfection. Fibers are polycrystalline materials of small diameters, whereas wires have large diameters. The common materials are graphite, silicon nitride and aluminum oxide, etc. Glass, polymers and boron, they fall under the category of fibers, right? So fibers are polycrystalline materials of small diameters, whereas wires have large diameters. The common materials are graphite, silicon nitride, aluminum oxide, etc. Glass, polymers, boron, they fall under the category of fibers. Steel, tungsten and molybdenum are commonly used as fibers. Next is, which of the following statement is true? Your options are higher grain boundary increases strength, or grain refinement increases ductility, composite strengthening is related to grain boundary, or single crystalline material has high grain boundary area. So correct answer here will be first one. Okay, so in case of a fine grain material, one that has small grains is harder and stronger than the coarse grain due to a greater total grain boundary area to restrict dislocation motion. Grain boundaries also act as sources and sinks of dislocation, but that is not the reason for hardness enhancement in metals. So here also you can see with different grains, they will be having different orientations. So this orientation is different compared to this one. There is large angle and small angle grain boundaries will be forming here, and these grain boundaries, they are the regions of disorders. So there will be defects will be higher, dislocation and vacancies will be higher in these regions, and they provide good diffusion compared to the crystalline region. Okay, then next is, and other options are all false. So all statements such as grain refinement increases ductility, it doesn't increase ductility, it increases strength. Composite strengthening is related to grain boundary. No, it is not related to that, it is related to dispersion. And single crystalline material has high grain boundary area. No, it doesn't have any grain boundary region. Next question is, the below figure depicts the structure of blank composite materials. So your options are discontinuous, aligned, laminate and dispersion strengthened. So correct answer here will be laminates. So as you can see, there are different orientation of laminates that are stacked above each other with the help of adhesives. Explanation. So a laminar composite is subcategory type of structural composite with a varying orientation for each layer. The composite materials are used for their high strength. Which of the following is correct size range of dispersoids in micrometer in dispersion strengthened composites? So your options are 0.0001 to 0.0009, 0.01 to 0.1, 0.1 to 1, 2 to 2.7 micrometers. So correct answer would be second. Dispersoids and composites, they vary in size from 0.01 to 0.1 micrometer. And they also have they are very small, and size is an important factor for mechanical properties. Fine size dispersoids provide better properties. And which of the following is not a characteristic trait of composite materials? High strength, toughness and modulus, lightweight, easy to assemble and sensitive to temperature change. So last one is also only the not a characteristic of composite material. So your explanation includes composite includes matrix plus reinforcement, and reinforcement generally provides a composite with more strength, stiffness and toughness due to crack bridging. Okay, and the composite materials have great mechanical properties, corrosion resistance, and they are easy to assemble, and they are light in weight in case of fiber composites, and they aren't very sensitive to thermal shocks and temperature changes. However, they are more expensive than conventional materials. Next question is, what type of material is often used in the creation of soft actuators for soft robotics? Your options are shape memory alloys, carbon fibers, nylon and aluminum. So correct answer will be first one, shape memory alloys. Okay, and the shape memory alloys, they work great as actuators for soft robotics, example nitinol. And the SMAs, they convert thermal energy into mechanical energy, making them desirable for making actuators. Next question is, chain polymerization mechanism may occur due to, your options are cationic, anionic, only due to free radical and cationic mechanisms, or all of the given options. So correct answer will be all of the given options. So free radical polymerization is a type of chain growth polymerization along with anionic, cationic and coordination polymerization. And free radical polymerization is a polymerizing approach by which successive addition of free radicals takes place in form of a polymer unit. Next question is, which of the following may alter the mechanical properties of reinforced? Your options are constituent properties, fiber length, fiber orientation and all of the mentioned. So the correct answer will be all of the mentioned. So here you can see constituent properties, fiber length, fiber orientation, etc. affect the overall property of reinforced composites. So with increasing fiber length, you can see only one thing, processability will deteriorate. Other properties such as modulus, strength and impact will keep on improving. Next question is a particle reinforced composites have which type of strengthening? The options are strain hardening, grain refining, edge hardening and dispersion strengthening. So correct answer will be dispersion strengthening. So in case of particle reinforced composites, the particles will be dispersed. So the interface won't be compatible with the matrix. It will be having sharper interface. So it will be dispersion strengthening. Which one is not a role of fiber in composites? To relieve stress, to enhance strength, to provide crack bridging or to enhance thermal resistance. So only one that is not a role of fiber is to relieve stress. So because of fibers there is always some strain field attached to presence of these fibers or reinforcements. So this won't be a role of fiber. Next question is which material has at least L by D ratio equal to 10:1? Your options are whiskers, fibers, rods and wires. So the correct answer here will be fibers. Okay, so fibers are the only ones that will be having this ratio. Whiskers have lesser of the length, and the diameter for rods and wires will be higher. Fourth question is what is the disadvantage of metal matrix composites? Your options are power operating temperature, flammable, costly or low resistance to organic fluids. So the correct answer will be costly. So metal matrix composites are costly compared to polymer matrix composites, and they are also metal matrix composites are non-flammable and their operating temperature is higher than PMCs, and they are also resistant to organic fluids. Fifth question is which is not an advantage of filtration method for fabricating composites? Your options are cheap dye requirement, automated processes, high speed or continuous reinforcement. So the correct option will be cheap dye requirement. Okay, because they require dye which is costly compared to other processes. Other processes require cheaper tools. So then we went through definition of composites. So natural or artificial mixtures of two or more distinct phases or constituents are known as composites, and the mixtures they may consist of metals, polymers and ceramics, and the primary engineering goal is to achieve a better balance of properties from the combination of materials. So these are made with the help of carbon-nomic sandwich, carbon monolithic structure, Kevlar-nomic sandwich, Kelvin-nomic sandwich with stiffening carbon plies, etc. Then in history also we can see use and development of composites and natural composites. So they exist throughout the nature. Almost all natural materials are made of composites. Some of the examples include wood, bones. So in case of wood you have lignin matrix plus hemicellulose bound in a spiral form. Bone, which is consists of organic fibers and inorganic crystals, water and fats. And 35% of bone consists of organic collagen, protein fibers with small rod-like hydroxyapatite crystals. And here you can see there are various parts of wood which are made with the different constituents. Next is cast iron as composite. In cast iron and steel you have graphite and Fe3C work as reinforcement in a metallic matrix, so both are composite like structures. Next is classification of composites. you have particle reinforced, fiber reinforced, and structural materials. So in case of particle reinforced, you have large particle and dispersion strengthened materials. And in case of structural, you have laminates of different direction and different orientation. So these can be unidirectional, these can be cross plied. And in case of sandwich structure also, laminates and sandwich structures are structural composites. Large particle composites, so the example include concrete, which is composed of cement, which acts as matrix, and also sand and gravel, which acts as particulates. The particulate phase is harder and stiffer compared to matrix, and the reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle, and the matrix transfers a fraction of the applied load to particles, and the improvement of mechanical behavior depends on strong bonding at the matrix particle interface. Next is dispersion strengthened composite. So here size of the particles will be smaller. Particles are normally much smaller with diameter ranging between 10 to 100 nanometer, and the strengthening occurs So in case of dispersion strengthened materials, particles are normally much smaller with diameters between 10 to 100 nanometer. The strengthening occurs on the atomic or molecular level. The matrix bears the major portion of applied load, while the small dispersed particles, they hinder the motion of dislocations. Thus, plastic deformation is restricted such that yield and tensile strengths as well as hardness improves. Examples include sintered aluminum powder. So, in this case, flakes of aluminum coated with alumina, which are dispersed within an aluminum metal matrix. And here also you can see the dislocation movement is hindered because of the stress field of the dispersion particles. And these particles are strong and size is lesser than 100 nanometer. The fiber reinforced composites. So in fiber phase, these fibers phase can be of three types: viscous, fibers, and wires. And on the basis of diameter and character, fiber phase can be grouped into three types: viscous, which are very thin single crystals which have extremely large L by D ratio, but they have the form of fiber. These flow free and they are extremely high strength, but they are expensive. And these include graphite, silicon carbide, silicon nitride, and aluminum oxide, etc. Fibers, a material which has at least L by D ratio equal to 10:1, and they are either polycrystalline or amorphous, and generally polymer and ceramics. Wires, these are relatively large diameter and their typical materials include steel, molybdenum, and tungsten. Now matrix phase. The role of matrix phase include binding fibers together to protect the individual fiber from damage by the external environment. They act as a medium to transmit and distribute externally applied stress to fibers. It also serves as a barrier to crack propagation. The role of fibers include to enhance stiffness, to enhance strength, and to provide crack bridging, and to enhance thermal resistance. And the requirements of composite: the matrix material should be ductile, and the elastic modulus of fiber should be much higher than the matrix, and there should be adequate bonding between the matrix and fibers. Stress strain curve. So here you can see different characteristics of matrix and fibers. So matrix should be ductile, so this is the stress strain curve of a ductile material, which will be having lesser of elastic modulus. Fiber should have higher elastic modulus, so fiber elastic modulus is higher and its strength is also very higher, but it is brittle. There is no plastic deformation seen here. And the composite will show properties in between these two phases. So it will be showing two stages, elastic and plastic region, and it will also be showing elastic modulus in between these two phases and the fracture strength in between these two phases. Next we went through volume and weight fractions. So these are just the fractions of fiber and matrix and void volume fraction. So entire volume of fiber divided by volume of composite will give you volume fraction of your fiber, and similarly it will be for matrix and void as well. All addition of all volume fractions will be equals to 1, and the volume of composite will be equal to volume of fiber, volume of matrix, and volume of voids. Weight will be also similar. Fractions addition will be 1, and then this weight equation can also be written in terms of density, and you will be getting rho c times vc equals to rho f times vf plus rho m times vm. Now loading can be in two types. It can be longitudinal. In this case the direction of fibers will be similar to direction of loading. Okay, and assuming perfect bonding between fibers and matrix, the strain in fiber, matrix and composite will all be equal. Okay, so here EF, EM, EC all are longitudinal strains in fibers, matrix and composites respectively, and the tensile load PC applied on the composite lamina is shared by the fiber and matrix. So PC equal to PF plus PM, therefore sigma C times AC equals to sigma F AF plus sigma M plus AM times AM. So here if you divide all this equation with AC, you can get this equation, and you can write it in terms of elastic modulus. EC equals to EF VF plus EM VM. The tensile load is acting normally in the fiber direction. Sigma F equals to sigma M equals to sigma C. So in case of transverse modulus, you are applying load perpendicular to the direction of fiber. The strain or deformation of the entire composite can be given with the EC equals to EF times VF plus EM times VM, and this can be rewritten using Hooke's law as sigma C upon EC. So strain, you have to just write the equation of strain. Okay, so elastic modulus you already know, sigma is given as E times E strain. So sigma C upon EC equals to sigma F upon EF times VF fraction of fiber plus sigma M upon EM times VM, which is volume fraction of matrix. Since sigma F equals to VM equals to sigma C, above equation becomes 1 upon EC equals to VF upon EF plus VM upon EM. So EC transverse will become EF EM divided by EF VM plus EM VF. Next we went through metal matrix composites. In this case, matrix is ductile metal, which is usually alloys of aluminum, magnesium, titanium and copper. All are ductile metals. And fiber can be made of So, in case of matrix, it can be made of ductile metals such as aluminum, magnesium, titanium, and copper. Fibers can be made of carbon, silicon carbide, boron, aluminum oxide, etc. Advantages of MMCs over PMCs include high operating temperatures, and they are also non-flammable because the polymer matrix in PMCs make them flammable, and they also have greater resistance to degradation by organic fluid compared to PMCs. But they have demerit to the MMCs include that they are costlier compared to PMCs. So as we know, polymers are cheaper compared to metals, so their composites are also cheaper. And these were some of the MMCs that we talked earlier as well. And their applications include tank armor, golf clubs, space shuttle frame, antenna boom for the Hubble Space Telescope, which includes graphite fibers in 6061 alloy of aluminum. And the polymer matrix composites. So glass fiber reinforced polymer GFRP composites. In this case, matrix will be made of plastics, most often epoxy and polyester resin. And the reinforcement include glass fiber or e-glass made of diameter having 3 to 20 micrometer, and typically 55% of silica, 16% of calcium oxide, 15% of aluminum, 10% of boron oxide and 4% of magnesium oxide. They are easily drawn into high strength fibers from the molten state, and their limitation includes service temperature up to 200 degrees Celsius, above which polymer matrix starts to deteriorate. Applications include automotive and marine bodies, plastic pipes, storage containers and industrial floorings. And these are the properties for the polymer matrix composites, consisting of modulus 45 GPa and tensile strength 100,020 MPa. CFRP, carbon fiber reinforced polymers. In this case, matrix will be made of polymer resin and fibers will be made of carbon fiber. Carbon is a high performance fiber material because they have high specific modulus, which is modulus divided by density, and the specific strength of all reinforcing fiber materials, and they retain this at very elevated temperatures also. And at room temperatures, they are not affected by moisture, and they have wide variety, and also they are not affected by wide variety of solvents, acids and bases. The fiber diameters are normally in the range between 4 to 10 micrometer, and the applications include carbon fiber wheel, Boeing 787 Dreamliner, nearly 50% frame of CFRP, mountain bicycle frame, seats, rackets, etc. The properties of CFRP include 1600 kg per meter cube density, tensile modulus include 145 GPa, tensile strength include 1240 MPa. Aramid fiber reinforced polymer, and its trade name is most common aramid fiber, are Kevlar and Nomex. And chemically, this group of materials is known as polyparaphenylene terephthalamide, and it is known for its toughest impact resistance and resistance to creep and fatigue failure. And they have strong covalent bond axially and weak hydrogen bond transversely. And they also have negative coefficient of expansion due to kinks, and they have UV sensitive, and also they degrade. Typical applications include ballistic products such as bulletproof vests and armors, sporting goods, ropes, missile cases, replacements for asbestos in automotive brake and clutch linings and gaskets. Ceramic matrix composites. So ceramics are highly brittle in nature, thus they have low fracture toughness. In general, the fracture toughness of ceramics is 1 to 5 MPa under root meter, while for metals it is 20 times this. By using CMC, fracture toughness can be increased to lie in the range of 6 to 20 MPa under root meter. Crack initiation normally occurs within matrix phase, whereas crack propagation is hindered by the particles, fibers and whiskers. And these also exhibit improved high temperature creep behavior and resistance to thermal shock. Now the brake disc of Ferrari race car is also made using carbon fiber reinforced in silicon carbide matrix. Cermets, these are the composites made with ceramic and metal. In this case, your binding phase is metal, and ceramics, they act as reinforcements. The composites of ceramic particles which are strong and brittle in a metal matrix which is soft and ductile. It has very high toughness and wear resistance compared to traditional materials. For instance, tungsten carbide or titanium carbide ceramics, they are embedded in a matrix of a metal such as cobalt and nickel, and only about 10 to 15% of metal volume will be in the cement. They are also used for cutting tools for hardened steels, and electrical components such as resistors and vacuum tubes and valves are some of the applications. Carbon-carbon composite. So in this case, both reinforcement and matrix are carbon, and these are very expensive. Also, these have very high modulus of elasticity, up to 200 GPa, and strength even retained at around 2000 degrees Celsius. And these have very low density as well, 1830 kg per meter cube, and they have very high thermal conductivity, 100 watt per meter Kelvin, and also they have low coefficient of friction in fiber direction, and they have low abrasion resistance. Applications include missile cones, B-2 bomber aircrafts, winged leading edges of the space shuttles. In case of laminated composites, a laminate is constructed by stacking a number of laminae. They can be of unidirectional laminate in which fiber orientation angles are same in all lamina, such as theta equals to 0 degree. Angle ply laminates. So in this case, fiber orientation angles in alternate layers are theta minus theta, theta minus theta, where theta is equal to 0 degree or 90 degree. Cross ply laminate. In this case, fiber orientation angles is in alternate layers are 0 degree, 90 degree, again 0 degree, 90 degree, which is shown here, cross ply laminae. In case of symmetric laminae, it is identical ply at 10 equal distance about the center line. Next is sandwich panel. So it consists of two strong and stiff sheet faces that are separated by a core material or structure. It combines relatively high strengths and stiffness with low densities. The outer sheet consists of aluminum alloys, fiber reinforced plastics, titanium, steel or plywood. Core materials include rigid polymer forms. Examples include phenolics, epoxy polyurethanes, wood, which is balsa wood, and honeycomb includes hexagonal cells. These sandwich panels, they have these advantages. So they have low water absorption, they have good anti corrosion, they have good thermal insulated capacity. So here also we can see in between you have honeycomb type of structure, then you have sheets which will be sandwich, used for sandwich structure. Next is hybrid composite. So two or more different kinds of fibers in a single matrix will be there. And for example, carbon fibers, which are strong and relatively stiff, and they provide a low density reinforcement, but they are expensive. Next is glass fibers, which are inexpensive, but they lack thickness of carbon. The glass carbon hybrid is stronger and tougher, and it has higher impact resistance. The fiber may all be aligned and intimately mixed with one another, or laminate may be constructed. The applications include baseball bat, ice skates, etc. Now there are some techniques for making these 5 techniques for making these composites. First is hand layup technique. Okay, so firstly we apply gel coat. Okay, gel coat is applied to open mold to avoid the sticking of polymer to the surface, and the reinforcement is placed in the mold. Okay, so here this dry reinforcement is placed. Then this resin is poured in this. Okay, so this gel coat will be providing separation, so it won't be sticking. And the base resin mixed with a catalyst is applied by pouring and brushing. The layup is made by building layer upon layer to obtain the desired thickness. For an epoxy based system, the normal curing time at room temperature is 24 to 48 hours. This method is mainly suitable for thermosetting polymer based composites. Advantages include low cost tools and versatile. Disadvantages include time consuming, inconsistency, and easy formation of air bubbles and disorientation of fibers. Spray layup technique. It is extension of the hand layup method. A spray gun is used to spray pressurized resin and reinforcement, which is in the form of chopped fibers. The matrix material and reinforcement may be sprayed simultaneously or separately. Advantages include continuous process. Any materials can be used as mold. Error can be corrected by respray. Disadvantages include inconsistency, no control of fiber orientation, and only one-sided finishing. And also it is not environmental friendly. Next is pultrusion. So it is automated process for continuous manufacturing of constant cross section profiles. And these profiles, they have high strength in land direction. Principal reinforcement include glass, carbon and aramid fibers from 40 to 70% volume. Matrix materials include polyesters, vinyl esters and epoxy resins. Advantages include that it is an automated process. It is high speed process. Versatile cross sectional shapes can be obtained. Continuous reinforcement is provided. And disadvantages include dye can be easily messed up. It is also consists of expensive dye requirement. It is mainly thermoset matrix is used in this particular process. Next is pre-preg process. In this case, the fiber reinforcements are impregnated with a specific amount of epoxy resin system in a separate step before the layup. In this so-called pre-pregging step, fibers are wetted uniformly and pre-preg of high quality is formed. Advantages include orientation of fibers can be changed, consistent, high productivity. Disadvantages include continuous process which needs more customers, limited shelf life and delamination. Resin transfer molding. This is the last process. It is also known as liquid transfer molding process. In this, dry fiber is pre-formed into the lower mold and the upper mold is fixed in place. Then low viscosity resin is injected under some pressure into the mold cavity where it spreads throughout the fiber. Advantages include design flexibility, low startup cost, faster production, good surface finish. Disadvantages include expensive tooling, time consuming curing and complex mold design. Okay, that's it from my side.